Hey, this is Horner, and we're going to look at 17.5, 6, and 7. 17.5 is about capacitors, and it's a pretty simple little unit here. There's some weird terms and things, but overall, it's really not that bad. So a capacitor is kind of like a battery, except for a battery uses chemical energy in order to produce a potential or voltage, and a capacitor is something that just stores that. Um, and it stores it by just separating positive and negative charges. So it's usually got a couple conductors in it, and between those two conductors is either air or some sort of material. And one of those conductors is positive, and the other conductor is negative. And because they're separated, you can actually allow an electric field to be able to move from one to the other, which is a pretty useful little device. This is a good example of some pictures of some capacitors. You'll see they're kind of these bulb things here. Um, this is a capacitor, and this is a pretty high power capacitor. You never want to get inside of any electronics device and play with the capacitors, because some of them can pack a pretty big wallop. Some of these are really thin capacitors. You'll see some of them around, more cylindrical. You've got another capacitor over here and another one here. So just kind of a good description of what they look like. This is another picture of a capacitor, so you can see the field that's around this capacitor, and you can see all the field lines. And remember we said that this side is high potential, this side is low potential, and so we're just storing charge within that. Work has to be done in order to separate the charges, so you have to use a battery whenever you, or some sort of charging device like that, in order to charge up that capacitor. So we have to charge those. So we say that work is done to do that. So it's just like if I have a ladder, I have to do work in order to get from the bottom of that ladder all the way up to the top of the ladder. So that stored potential you've already seen is associated with electric field, and we can get all that energy out by letting those charges come together again. So if I climb to the top of the ladder, if I want to lose that energy, I jump down, and then I can climb the ladder again. So basically works in the same type of way. The simplest form is called a parallel plate capacitor. Has a couple of parallel metal plates, and they each have an area, and they're separated by a distance. So we can put charge positive Q on one plate and charge negative 2 on the other, and we just see that there's air between the two. If you hook a battery up to a capacitor, it removes electrons from one plate, leaves it positively charged, puts them on the other. So what we're doing is just having that battery do all the work in order to make the electric potential energy higher in that capacitor. So we're taking chemical energy and just converting that chemical energy. So we're going from this one to this one. Pretty easy process, not a lot to it. In general, that field between the two plates doesn't really have to be uniform, but because they're so close together, it typically is. So the plates in a real capacitor are almost always close enough that we can say that there's not a lot of edge effect here, like you see at the edges. You don't really have a lot of that. You just have these really nice linear parallel lines. If I go through and look at the magnitude of the charge Q and it's spread over the plate, surface A, then I can talk about something called surface charge density. So that's just the amount of charge per unit area, and it's denoted by this symbol, and this is the Greek letter sigma. And so if I have a couple of plates, so there's one plate, and we'll make it in 3D, and then if I have another plate behind it over here, okay, so then I can think about the charge per unit density on one of those plates. All right, so that's a little bit about charge per unit density. In problem 68, which we're not going to do, you can show that the magnitude of the electric field just outside the conductor is equal to E, and this is 4 pi, and then K, and then we've got our, if we go back, we've got our sigma here. Remember, that's the charge per unit density, so that's our sigma. So here's our sigma, and then we've got this funny looking symbol here, and we'll talk about what it is in a little while, but we're really more worried about what is the value of this number, and the value of this number is a constant, and it's 8.85 times 10 to the negative 12th coulomb squared per Newton times a meter squared. Okay, so this is a good equation to give you that electric field. So since we know that we have a uniform electric field, the magnitude of the potential is just V is equal to ED. And because that field is proportional to the charge and the potential difference, we can say the charge is proportional to, so the charge that we have is proportional to the potential difference. So this is good for any capacitor, not just a parallel plate capacitor. So when you look at all times of different capacitors, you'll see that. So in essence, what we can say is the charge, magnitude of the charge, is equal to the potential difference times this constant of proportionality, and we call that capacitance. So there's your capacitance and a capacitor. The SI units for capacitance are coulombs per volt, so that's a C over V, and that's equal to a farad. Most of the time we don't deal with just farads, we usually do microfarads, which is 10 to the negative 6th. Ooh. 10 to the negative 6 farads. Sometimes we'll do pico, nanofarads, just kind of depends on the application that you have. So that's your definition of capacitance. We can now find the capacitance of a parallel plate capacitor. So here we've got the electric field is equal to sigma over that constant, and we can also then say that that's Q over the constant times A, and if the plates are at a distance d apart, then the magnitude of the potential difference, so we're looking for the magnitude of this potential difference, we know is ED, but that's just QD over epsilon naught A. And if we rearrange, we can rewrite this in the form of Q is equal to that constant times A all over D times the change in the voltage. So that's just going through and finding charge. So if we compare this definition of capacitance, the capacitance of a parallel plate capacitor is just A over 4 pi times K times D. On 17.9, this is a good example. In one type of computer keyboard, each key is attached to a parallel plate capacitor. So down at the very bottom is your parallel plate capacitor. And the other plate is fixed in position. So you've got a movable plate and a fixed plate. And essentially what happens whenever you hit that key, the top plate moves closer to the bottom plate, and that changes the capacitance, and that causes a little bit of charge to flow through the circuit. So let's say that we have a square of size 6 millimeters, and the plates separate. This plate separation changes from 4 to 1.2 millimeters when a key is pressed. How much charge flows through the circuit? And then they want to know, does the charge on the capacitor increase or decrease? And we can assume there's air between the plates. And one thing that they do is they do have this capacitor, and it's maintained by a 5-volt external circuit, so we have to have some sort of potential source there. The strategy here is just to use our equation, and we can find the capacitance from this equation, and then the charge can be found by just using C times that potential difference across those plates. So in this problem, we want to know what is the final minus the original charge. And so we can say this is the final capacitance times the change in voltage minus the original capacitance times the change in voltage. We said capacitance is A over 4 pi K times D final, so that's your final separation, minus A over 4 pi K D, that's the original separation. And so they've simplified the equation a little bit. They went ahead and found the area here, multiplied times that potential, and then divide by 4 pi, and then remember K is just 9 times 10 to the 9th, really simple. So we're just using the same types of things we have before. Just looks a lot more difficult, but it really is not. And then we just have 1 over that final separation and 1 over the original. And do notice that these are in meters and not in millimeters or centimeters. So when we're done, we get 9.3 times 10 to the negative 13th coulombs, which is 0.93 pico coulombs, and pico here means 10. to the negative 12th. Since the delta Q is positive, the magnitude on the charge of the charge on the plates does increase. If it was negative, then we would know that the magnitude of the charge is decreasing. And that's the solution for 17.9. A good application of capacitor is using a microphone. So here you've got a couple of plates. The first plate moves, and as it moves in and out, it changes the space between the two plates, and so your capacitor changes. That is then sent to a little processing circuit, and then that helps tell all the electronics what's going on so that you can hear your voice a little bit louder using that microphone. For 17.6, this is about dielectrics, and before we said that between two plates, usually we have air. And the problem with air is it makes it really easy for the plates of the capacitor to discharge, and so a spark will jump across the two. So what we do is we like to put a material in between the two that kind of helps us not have discharge. And there's all kinds of different materials that you can put between them, but those materials help us form this dielectric. So on the next slide, this is just talking a little bit about these insulating materials called dielectrics. They can withstand electric fields larger than those that air has, and because air allows that to go through and create that spark, we really want to use dielectrics in our capacitors. So another advantage of placing a dielectric between the plates is that we can increase that capacitance, so we can make capacitors have higher and higher values. For a parallel plate capacitor, that dielectric, we have a Greek letter called kappa, and that's the dielectric constant. So you'll notice that we have the same equation we did before, but now we've added this thing called the dielectric constant, and all it does is it helps increase. So you'll remember this number will be positive. It'll help increase the capacitance of our capacitor, which we know the capacitance is here. So just a pretty simple little thing to do. The dielectric strength is the electric field strength at which the dielectric breakdown occurs. So the higher that higher the value, the higher the dielectric strength. We know that the change in potential is equal to ED, and so the dielectric strength determines the maximum potential difference that can be applied across a capacitor for every meter of plate spacing. So we're just trying to make these capacitors stronger by putting that dielectric material in. Lots of different dielectric constants here. You'll notice that air has a dielectric constant about 1, so that makes a strength about 3. If we have paraffin paper, it's kind of a wax paper is all that is. It increases the strength from anywhere from 40 to 60. You'll notice Teflon is about 60. Rubber can be anywhere from 16 to 50. Paper is only about 8. And then mica is kind of a sandy material, and it's anywhere from 150 to 220. So be really careful that you don't confuse the dielectric constant with dielectric strength. Okay, they're not related. But we do have pretty high dielectric strength here. You'll notice the values, but be careful because see, Teflon is got a dielectric constant of 2.1, but the strength here is 60. But this is a higher dielectric constant, but the dielectric strength is only 8. So be careful that you don't equate the two in any way. For the next part, we're going to talk a little bit about how a dielectric works. The notes here, you don't have to fill anything out, you just kind of want to pay attention to what's going on. So remember, polarization is just separation of charge. So if I take a charged rod and I get it near an atom, I can polarize that atom, kind of flip it from one place to the other. And you'll notice that it's still neutral, but the center of positive charge no longer is in the center of negative charge. They're now separated on both sides. If I take a plate, so the charges on capacitor plates induce a polarization of dielectric. So here's that insulating material, and remember the charges are not free to move very well in those. So we have a polarization of the atoms within the material. So the positive charge is slightly displaced relative to that negative charge. throughout the bulk of the dielectric, there's still equal amounts of positive and negative charge. So the net effect of polarization is to just really have a layer of positive charge on one face. Okay, so here's our positive charge on one face of the dielectric. Here's negative charge on the other face. So each conducting plate faces the opposing charge on that plate. So here's positive charge, and then we've got the negative part of the dielectric, and then vice versa on the other side. The layer that does oppose the charge induced on the surface helps the dielectric attract more charge than it did if it didn't have the dielectric. So capacitance is charge per unit potential difference, and therefore our capacity or capacitance must have increased because of that. The dielectric constant material is a measure of ease with which the insulating material can be polarized. But remember, that constant is not the same as what we were looking at before when we talked about the strength. Okay, so be really careful that those two are not related. For the next part here, we just kind of see what happens. With a weaker field, there's a smaller potential difference between the two, so a smaller potential difference makes it easier to put more charge on a capacitor. And that's just just another way of trying to make it a little bit stronger of a capacitor. So if I have a dielectric and I immerse it in an external electric field, okay, the definition of dielectric constant is the ratio of that electric field in a vacuum versus the electric field in that external dielectric itself. So if I want to know what the electric field is inside the dielectric, I just take the EO or the E naught is what they call that, and divide it by kappa, which is that dielectric constant. Here's a good example. I have a parallel plate capacitor. It has plates of 1 meter squared in area and a spacing of 0.5 millimeters. They want us to then see that the insulator has a dielectric constant of 4.9 and a strength of 18 kilovolts per millimeter. So they first want us to find the capacitance, and then they want us to find the maximum charge that can be stored. So finding the capacitance is easy as long as you know A, which is the area and the distance between the plates, and then we have our dielectric constant for this material. So they've basically just plugged everything in using the right units. Be careful, this was 5 millimeters. Here we've got 1 meter squared, and we end up with 8.67 times 10 to the negative 8th farads, which is about 86.7 nanofarads. Nano, remember, is 10 to the negative 9th. So to find our change in voltage here, or change of potential, we just took that 18 kilovolts per millimeter, that's the field strength, times that separation, and we get 9 kilovolts. And then finally we can find the charge that's stored on the capacitor by just taking the value that we got for capacitance and multiplying it times the voltage. So now we end up with 7.8 times 10 to the negative 4th coulombs. So a pretty easy problem. Just don't let all the funny symbols scare you a little bit there. A neuron is very similar to a parallel plate capacitor, and the membrane serves as that dielectric. So what they want us to do in this problem is just find the capacitance of the neuron and the number of ions, assuming that they're all singly charged, required to establish a potential difference of about 85 millivolts. We can say that this cell membrane has a dielectric constant of about 3, a thickness of 10 nanometers, and an area of about 1 times 10 to the negative 10th square meters. So yes, your cells do this. We know we know kappa, we know A, and we know D, so we can just find the capacitance. Then from the potential difference in the capacitance, we can find the magnitude of the charge. And a singly charged ion has a charge of E, so Q over E is the number of ions on each side. Here we go. There's our really simple equation. Again, just looks tough. 3 was our dielectric constant. Be careful with your units. Make sure everything is in meters. And we end up with about 0.27 picofarads, so a really small amount of capacitance there. The charge is equal to our capacitance, so there's our capacitance again, times the voltage, and we end up with about 0.023 picocoulombs of charge. If I take that number of coulombs and divide it by 1.602 times 10 to the negative 19th coulombs per ion, I get somewhere around 1.4 times 10 to the 5th ions. The thunderstorms that you see typically in the spring and the summer in Indiana is very similar to just kind of looking at dielectric. So this is a large thundercloud. You'll notice that I have positive charge on top. I have negative charge on the bottom. And then the cloud and the water and all the other dust particles inside make up your dielectric. And that dielectric should have a value K, kappa. As that charge starts to get separate a little bit more. This is like a big capacitor, and now we're trying to create a path from the lightning cloud or from the cloud itself down to the ground, and this is where we get a discharge of all the stored up energy that's on the inside of the cloud. Once that happens, we do move charges from one place to the other, and we end up with that light flash, and a lot of the energy is associated with it. So just a really big giant capacitor is what we're looking at in that thunderstorm. The last section that we're going to look at is just the energy that's stored in a capacitor, and the energy in a capacitor can basically just be found by summing the work done by the battery in order to separate the charge. So if I know how much work the battery does, I know how much charge there is on the capacitor, and therefore I know how much energy there is in that capacitor. So when we look at this process for instant of time, when one plate has charge Q initial and the other one has a charge of negative Q initial, because remember the two plates should be oppositely charged, we know that potential difference between the plates is the change in potential, and that's equal to that original charge divided by our capacitance. If that Qi is really small, then what we can do is we can say the change in potential energy is equal to the change in charge times the voltage. And so therefore we can just say that the potential is equal to the sum of the changes in the potential energy, and that's equal to the sum of the charges times the voltages, which makes it really kind of easy. The energy in a capacitor, if you plot the velocity or the change in potential, sorry, not velocity, but change in potential here versus the charge, and then find the area, that will tell us what that energy is. So it's just 1/2 of Q times delta V. And we can do this for little tiny areas too, but here they've done it for the larger triangle. In 17.12, this talks about fibrillation. It's a chronic pattern of heart activity that's ineffective at pumping blood, and it's really life-threatening. So we can use a defibrillator in order to shock the heart and get the heart beating again correctly. So it basically just discharges a capacitor through the paddles on the skin, and that way we can get some of the charge to flow through the heart. So if I have an 11 microfarad capacitor and it's charged about 6,000 volts and then discharged into the patient's body, we want to know how much energy is in that capacitor, and then we can figure out how much charge goes through that patient's body if the capacitor discharges 100% or completely. There's about 3 different expressions for energy in a capacitor, and since the capacitor is completely discharged, all of that charge is going to go through the patient's body. So here's our energy equation. It's just 1/2 Q V, which is the same thing as 1/2 the capacitance times the change in voltage. Times the voltage, and so here we've got 1/2 of the capacitance times the change in voltage squared, or the change in potential squared. If we can go ahead and plug our numbers in, we'd have 1/2 times 11 times 10 negative 6 farads, microfarads, times 6 times 10 to the 3rd volts squared, and we get about 198 joules. They wanted us also to figure out the amount of charge, and that's just C times delta V. And so here we take our capacitance times that change of potential, we get 0.0660 coulombs. Energy stored in a field, so we know that potential energy is energy of interaction or field energy. So remember, if I'm standing at the top of a big tall building, I have lots of potential energy. If I have a battery and I have positive on one side, negative on the other, I have potential between those two ends of the battery. Same thing with our parallel plate capacitor. I have energy stored in that capacitor until I discharge it. There's my dielectric. We can use energy stored in a capacitor to calculate how much energy per unit volume is stored in an electric field E. And they want to know, why do we do energy per unit volume? If I have 2 capacitors and they have the same electric field, they can store different amounts of energy. The larger capacitor stores more energy proportional to the volume of space between the plates. So that's why we're really looking at energy per unit volume. For the equations that kind of go with this, in a parallel plate capacitor, we know this is the equation for energy. We can kind of flesh that out. Here's our capacitance again, and then here's our change in potential squared. If that field is uniform, I can put ED in for my delta V, and now I have 1/2 kappa, then I have AD over 4 pi, there's our constant K times E squared. And our energy density then, or the electric potential energy per unit volume, is just U, little u, so that's energy density, and that's our potential divided by the area times the distance. Plug in our other equation that we had for that, and then we end up with the equation that you see here. And that is the equation for energy density U. And that is the end of this section.